Morning, everybody. All right. Hey, I'm going to show you some really cool circle theorems. This is technically 12.2 day one. Yes, 12.2 day one, but I'm going to go back to a couple 12.1 ideas too. I'm sending you this sheet of paper. This sheet of paper has, it's got a bunch of theorems on it, and it actually goes like this together. And then you can practice drawing if you feel like it. If you think this makes sense, you don't have to worry about it. But what I've got is all these theorems from 12.1 and 12.2 together with a bunch of circles that you can just sort of practice them on, or you just go ahead and do them on the practice questions that come up, which are pretty cool. So the thought is, what is actually true when you do certain things? The circles, you remember like this first one, if a line is tangent to a circle, it's perpendicular to the radius. And we already knew that one from the other day, from last week. So if you got a nice tangent line that it's perpendicular to the radius. Ooh, I like this pen. Okay, so that's the first one. There is number one, and that's our little 12.1, 12.2. I'll just kind of call these, I'll call this Roman numeral 1. Roman numeral 1, there's that picture right there, if you're going back for reference. Okay, so Roman numeral 2, hey, and if the line is perpendicular to the radius, that means that it is the tangent. So this is a backwards forwards one, where the conditional statement and its converse are both true. Now this guy, if two tangents to a circle are from the same point, we did this one the other day too. If you have two tangents from the same point, then they have to be congruent to each other. And that's kind of a nice one too. Very, very useful with some problems. That's kind of a cute little one right there, which is good. But now we get into a little bit interesting things. So this is the bulk of today. We're going to be talking about different theorems if you have congruent angles and arcs and everything inside. So there's going to be a couple of vocab words that come your way here. This is picture 3. Okay, this says congruent central angles have congruent intercepted arcs. Now that kind of makes sense. So let's say, I'm just going to use vertical angles for a minute to kind of help us. So let's say you have two angles. Oops, I missed. Two angles that are both central angles and they're congruent to each other. Hey, what do you know? The arcs that they intercept are congruent. And this is kind of cool. So like if these two angles are the same, these two arcs are the same. Of course, then these two angles would be the same as well because they're vertical or linear pairs to vertical. So these big ones would be the same as well. So you can imagine if these are like, if this is like 25 degrees right here, this arc would be, and so would this because they're central angles. So this goes backwards and forwards. So if they give you congruent arcs, you know that the angles, the central angles are congruent as well. And that's kind of cool. But then the next one, number 4, and you're going to see some similarities here. Number 4 says, if you've got congruent central angles, then they have congruent intercepted chords. And that's what I'm going to do a little bit differently. So let's say I just have like an angle like this that has a certain, whatever, degree measurement inside. And then I got another one that's not vertical, of course, because these don't have to be vertical. But let's say these two are the same. This is picture 4. Now we already know that the arcs are the same because that was the last theorem. But now it's saying that the intercepted chords are the same too. Now a chord, this is a new word. So a chord, I'm going to go over here to my basic circle picture, which I don't have yet. So here we go. Circle, not great. Okay, so we know we have our radius. There's our radius. There's our diameter. But if you have anything that just cuts through and basically a line segment that goes from one part of a circle to another part of a circle, this is called a chord. But you say, well, the diameter does that too, which is good. But the diameter is actually a chord. A diameter is a chord. Actually, a diameter is the biggest chord you can possibly have. If you have a chord getting bigger, smaller, that's why they call the diameter the great chord, because it's the biggest chord possible. But any cute little segment that connects one spot to another spot on any circle, this is called a chord. Okay. We have other words, of course, too. We have tangent, which we already knew. There's other words coming in too. I don't think we're going to get to this one today, but if you have a line or a line segment that slices through twice, like this, this is called a secant line. A line that crosses through twice. So a chord, a secant, a diameter, a radius, and a tangent, all very important parts of a circle. So I go back to here and it says, if you have congruent central angles, you have congruent intercepted chords. So I need to draw the chords. That means this guy would be the same as this guy. So these two would be the same. Well, we already know that these arcs are the same as well, which is kind of cool. So number 5, and here we go again with the same sort of thinking. Hey, if you have congruent chords, did you know they're congruent intercepted arcs? Well, now there's no central angles at all. So let's say somebody just sort of gives you, oh shoot, those don't look the same at all. Okay. Let's say somebody gives you, well, this is going to be kind of cool, actually, live correction. Let's say this one's like 3.2 millimeters. That one is definitely not. Okay, so let's make another 3.2 down here somewhere. Ooh, there we go. This will be decent-ish. Okay, there's another 3.2-ish. Okay, so hey, look. These two chords are the same. Well, guess what? If these two chords are the same, that means their intercepted arcs are the same as well. But we don't even need the central angles at all, and that's okay, because these are independent of the central angle. But of course, there is a central angle there. So the cool thing about this is we could do one picture all together, where let's say we've got some angle that's here, that's a certain amount. I keep using 2. I should use 3. And then we got, like, let's just for fun make this a diameter. It doesn't have to be, of course. And we've got another one that's kind of sprouting off this way that is the same. Now these two are the same now, let's pretend. So if these two central angles are the same, not only are their intercepted chords, their intercepted chords the same, but their intercepted arcs are the same as well. And there's all 3 of those theorems all in one, which is pretty darn great. And lots of great application questions you're going to see with that pretty soon. Okay, now the next one says, if your chords are equidistant from the center of the circle, they are congruent chords. And you're like, what? Chords equal? Let's think about these words. Chords we know. Equidistant is a nice word, just it means equal distance. If 2 chords are the same distance from the center of the circle, then they are congruent. If 2 chords are congruent, then they are equidistant from the center of the circle. So you've got some chords that somebody goes, hey, I'm just going to make these look the same. Hey, look, these chords are the same distance from the center. Now, this is interesting to say distance. Distance has to be perpendicular. Distance has to be perpendicular. If you're figuring out how far something is from, if I was to look at like a point, I'll do this in a different color, like a purple point down here, and say, how far is this point from this circle? I'm gonna go to the perpendicular. I'm actually gonna go directly to it, to the tangent line, and that will be how far away it is. So this is saying if 2 chords are the same distance from the center, guess what? They have to be the same length, which is actually really cool. So I'm going to do some interesting marking here as well. And this will lead us to the next one, because the next one says if a diameter is, oh, and by the way, if you're the same distance from the center, they're congruent. But if I go over here and say, oh, these ones were congruent, remember these 2 chords were the same length as each other? Well, guess what? If you put your center in here, this distance here would have to be the same as this distance here, because they're the same chord length. So if this was like 3, this would be like 3 as well, which is kind of cool. Perpendicular distance, of course, perpendicular distance. Now, this 7th one, we're doing a lot. The 7th one, if a diameter is perpendicular to a chord, guess what it does? It bisects the chord and the chord's arc. This is very interesting. Very interesting. Oh, to be Euclid, to figure these things out ourselves, eh? Okay, if a radius, now I'm going to stop it there for a second. That's not a full radius, right? If a radius is perpendicular to a chord, then it bisects the chord and the arc, whoop, 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 which kind of makes sense. So let's say somebody said to you, hey, I got this segment that's cutting through this chord and this arc, and it looks like it's making them congruent. Well, what do you know? It's going to be perpendicular. So that's a nice 90-degree generator. That's another nice way to make a right angle if you ever need to make a right angle. So congruent, chord splitting, and arc splitting by the same segment. Guess what? That's the radius or diameter, of course, if you keep it going. And this last one we won't really talk about today, but we used this one when we did our Euclid the game or whatever. We were on Euclidia.xyz. It's really cool. It just says, you want to find the center of a circle? You want to find the center of a circle? If you find the perpendicular bisector, I should do this with compasses. Hey, let's find the perpendicular bisector of that chord. I'm doing this just freehand. Perpendicular bisector. Perpendicular bisector. Hey, let's find the perpendicular bisector of this one. Perpendicular bisector, and your perpendicular bisectors always cross at the center. You could do it 100 times, and all of the perpendicular bisectors of all of the different chords. If you're ever in a bind for how do I find the center of the circle, I guess what you would do is just, if you had paper, you could just like fold it once to get a diameter, fold it twice to get another diameter, and voila. And that's probably your simplest, nicest way to find the center of a circle. But with constructions, you would find the perpendicular bisectors of two chords, and of course they would all agree. So there's a bunch of stuff there, kids. There's 8 different little theorems that have to do with circles and chords, but they're going to ask you a lot of questions about those, and hope you enjoy just some basic truths. We're going to practice this all week. Basic truths about what happens with circles and chords and intercepted arcs. All right, thank you.